Hey everyone, welcome to day 2 of the antiderivative. When you find the antiderivative, just as a reminder, that is the process called antidifferentiation. So you may hear the term antiderivative sometimes, you may hear the process antidifferentiation, but it's all meaning the same thing, okay? So I just wanted to, just make a note of that. We are still dealing with our indefinite integrals from yesterday, but today we're going to learn a couple of tricks related to polynomials. First one is multiply or distribute. The second one is to separate fractions. And just as a side note, when we did our derivative process, we actually used these same tricks with polynomials in order to create an easier derivative process. And so now we're going to use those tricks to make an easier antiderivative process. So hopefully as I'm going through these two tricks, you'll kind of recognize them from class, I know it was a couple months ago, but from when we were finding the derivative of these types of problems. So first trick is to multiply or distribute. So I have an example here that I want to take the antiderivative of the product of x plus 2 times x minus 5 dx. Now, we talked about yesterday that if you have a polynomial that you're taking the antiderivative of, let's say just something like this, you take the antiderivative of each term separately. Well, the issue here is that even though I have a term, the issue is right here. I have multiplication happening there, right? Multiplication. And so that doesn't make this a polynomial anymore. This is the product of two polynomials. So I need to get this into a form of just a term plus a term plus a term plus a term plus a term rather than having that multiplication component in there. So in order to do that, we are going to multiply or distribute. So what we're going to do is we're going to go back to that original problem, and we're going to just FOIL this, right? We have a binomial times a binomial, so let's FOIL. So in FOIL, we do the first, so x times x is x squared. We then do the outer two terms, so x times negative 5 is negative 5x. We have the inner two terms, and then we have the last terms. Okay, so now once we clean this up, we have x squared, negative 5x, and a positive 2x is negative 3x, and then we have that negative 10. So this is now our new polynomial that we're going to take the antiderivative of with respect to x. So now that I have my equation in this format, all the terms are just being added or subtracted together. There's no multiplication happening between a polynomial and another polynomial. So now we can go back to our rules from yesterday and utilize especially our power rule, which as a reminder was if we take the antiderivative of x to any power, you're going to have x to the, oh, that's not an x. You are going to have x to the n plus 1 power. You're going to add 1 to the exponent. When we take the derivative, you subtract 1. So when we take the antiderivative, you add 1. And then we also have to divide by that exponent. Okay, and we can never forget that we're going to add that plus c there at the end for our indefinite integral. So let's go through the process now for this polynomial. Well, the antiderivative of x squared, we add 1 to the exponent and then divide by the new exponent. For our next term, the antiderivative of negative 3x, well, as we talked about yesterday, any sort of coefficient stays during your derivative or antiderivative process. And now all I have to figure out is what is the antiderivative of x? Well, that's x to the first power. So again, using our power rule, we are going to add 1 to the exponent, and then divide by that new exponent. And then finally, the antiderivative of negative 10. Well, we talked about how the antiderivative of any constant is that number times x. So we're going to add an x here. So we have negative 10x. And then again, we cannot forget about our plus c. All right, now none of these terms can really be simplified at all. Nothing can cancel out, so that is our answer. And again, if you're ever not sure if you did it correctly, well, you can take the derivative of this function and see if you end up back where you started with that polynomial. Okay, let's try another. All right, here's example 2. I want you guys all to jot down this problem and then pause the video for a second. I want you to try this one out on your own. All right, so take a moment, pause, and we'll come back in a second, and hopefully you'll have the same answer that I do. All right, so how'd you guys do? Well, I ended up with 2x cubed over 3 minus 5x squared over 2 minus 3x plus c. So I'm hoping you guys were able to successfully get there. You can see, again, we used our FOIL process. You can see my first, outer, inner, and last terms. I just want to make note in this step right here. Some of you guys may be asking why I'm including these parentheses. Because it's just a polynomial, so it doesn't really matter. Nothing's being multiplied by it. That's really more just a way that the antiderivative is written. Remember the other day how I was saying that something like this could be rewritten as the antiderivative of 2x squared dx minus antiderivative of 5x dx and minus the antiderivative of 3 dx, right? Because we're taking the antiderivative of each term separately, it could be written in this more drawn out manner. So we don't have to write it that way. Again, as you see, I don't write it out in that long way. But when we come back to this polynomial, we kind of have to show how each term has that dx attached to it. So if I did not have the parentheses here, right, it would sort of almost look like the dx was only attached to the negative 3. And we don't want that, right? We want all of the terms to be shown that they have that dx component attached to it. And so that's why we kind of write those parentheses there around a polynomial. So if you haven't been writing them, that parentheses in, it's a good idea to do it. If you just have the antiderivative of one term, like all these examples over here, no real need for the polynomial because the dx is already attached right to the individual term. But if you have, a few terms, more than one term with pluses and minuses in between, you really should start getting into the practice of having those parentheses around the entire function. Okay. All right, let's do one more example in our multiply and distribute section. And again, I'm hoping that you guys, some of you at least are recognizing this process from when we did the derivative. It's a lot easier to take the derivative of a polynomial rather than, something that looks like this, where we would have needed that chain rule process that all of you guys loved so much. But anyway, so in this case, we have 3x minus 1 quantity squared. Well, let's not forget that if I have a function as 3x minus 1 quantity squared, can't that just be rewritten as 3x minus 1 times 3x minus 1? Right? Isn't that the same thing? So now once we take that and expand it out, using the process that we just did for our last two problems, we should end up with our correct answer. So again, take a moment, try and come up with your answer, and I'll check back in a little while and see how you did. All right, how did we do? Well, as you can see, again, I went through my FOIL process, came up with the fact that our trinomial after we FOIL would be 9x squared minus 6x plus 1. I have the parentheses around that term, again, as we just talked about, because this dx here really should be distributed to every term within that polynomial. When I take the antiderivative of each term, again, I'm going to add 1 to the exponent of the variable and then divide by that new exponent. So antiderivative of 9x squared is 9x cubed over 3. Antiderivative of negative 6x is negative 6x squared over 2. Antiderivative of 1 is x, and we cannot forget about our plus c. Now, if you wrote this as your answer, again, if it's a short response question, that is completely accurate and acceptable and totally correct. But again, just thinking ahead to, I'm assigning delta math problems, and, if you see multiple choice problems eventually, they are going to simplify, simplify that 9 over 3 to just 3, the 6 over 2 to a 3, and so this one right here really is your best answer. Okay? All right, let's move on to our second polynomial trick, and that is to separate fractions. Now again, as I've mentioned, just like the first trick, the second trick, we also did the same trick when we were taking the derivative of a function that looked like this. Okay, in this case, for the derivative, I would have had to use a quotient rule. Not always the most, or not everybody's always first choice using the quotient rule. Same thing with the antiderivative. There's no quotient rule comparable for the antiderivative. I can't use a quotient rule type thing. So we need to separate the fractions. And what do I mean by that? Well, we are going to separate the fractions. So that means that I'm going to take each term in the numerator and divide it separately by the denominator. And again, I apologize if my handwriting is not the neatest. I'm doing my best with my fingertips. So I've separated all of them so that each numerator is divided by that denominator. Again, I have those parentheses around because I need every term to be attached to this dx over here. And now that I've separated them, I can simplify each of these fractions. So 5x to the 4th divided by x can just be rewritten as 5x cubed. Minus 2x cubed divided by x can be rewritten as 2x squared. And plus 4x squared divided by x is just 4x. And so after I simplified each of those fractions, now I just have a polynomial and I use the power rule. I no longer have to deal with that denominator, so it makes this problem a lot easier for me. So now we're going to take the antiderivative of each term individually. So the antiderivative of 5x cubed is going to be 5x to the 4th over 4 minus the antiderivative of 2x squared is going to be 2x cubed over 3 plus the antiderivative of 4x is going to be 4x squared over 2, and not forgetting about our plus c. And so I would probably just clean up this final term a little bit. Right, the 4 and the 2 could simplify just to have a 2x squared there as your coefficient. And then I would have that as my final answer, simplified. Right. Let's do a second one. Here we've got, again, another one where we see that denominator. And what's really important with these problems is we can really only do this when we have a monomial in the denominator. If my denominator was like x plus 2 or 3x minus 4, then this process of separating the fractions would not work. This only works when we have one term in the denominator. So I want you guys to start on this. See if you can just do the first step for me. Two steps. First 2 steps. I want you to separate and I want you to simplify. Okay, so separate the fractions and simplify your fractions, and then come back and see if you simplified it and got to the same point that I did. Okay, so we'll see you back here in a couple of minutes. All right, did you get to the same spot that I did? 3x squared minus 2x minus 1. The reason why I wanted to check in a little sooner than with our final answer is because of this term right here. So often when we're doing these problems, a lot of people will just look at this last term and see x squared divided by x squared and go, oh, that cancels, and then, need the eraser, then they don't write anything. They're like, oh, well, it just cancels out completely, so nothing is there. That is not correct. All right, don't forget, when something cancels out, when you have something divided by itself, that simplifies to a 1, not to nothing. All right, so we have to make sure that we have that 1 there as our place value, because that still is a term. Okay, it didn't go to 0, it just simplified to 1. Or actually, in this case, a -1 because of the subtraction sign in front of it. All right, now from here, if you would, take a second to finish this out and come up with your final answer. All right, and here we are. X cubed minus x squared minus x plus c. That's our final answer. Okay, again, in the step before, we had a 3x cubed over 3, so the 3 simplified, the 2 simplified, and so all of our coefficients in this case end up being just a 1. All right, let's go to our final problem for the day. Okay, so I have the antiderivative of 6x squared plus 8x minus 3 all over x to the 4th power dx. All right, so let's start with the same process. We are going to separate each term. So we've got 6x squared over x to the 4th. Oh, that was not a nice looking 4. Over x to the 4th. Wow, my 4s seem to really be struggling here, guys. Tough one. All right, that one looks better. Plus 8x over x to the 4th minus 3 over x to the 4th. And everything in parentheses attached to that dx. All right, now when we simplify, we have to remember that when we're dividing two things with a common base, you're subtracting those exponents. So in this case, x squared divided by x to the 4th, well, 2 minus 4 is -2. So this is going to simplify to 6x to the -2nd power, because again, x squared divided by x to the 4th, that's equal to x to the 2 minus 4 power, which is x to the -2nd. Plus, same thing with the next term. We got 8x to the 1st divided by x to the 4th. Well, 1 minus 4 is going to be -3. And then finally, for our last term, again, we have to be careful here. The 3 is going to stay. I don't have a variable up there, but this is really x to the 0 power. So x to the 0 divided by x to the 4th, 0 minus 4 is -4. And you know what? If you don't really like thinking about it that way, the other way to think about it is just simply, all right, I have a 3, and I have to bring this term up to the numerator. Well, bringing that term up to the numerator is going to change it to x to the -4th power instead of x to the +4th. So either way you want to think about it, either, kind of inputting that x to the 0 or just bringing the x to the 4th term up, either way you're going to get to the same spot. Okay, now we're dealing with a lot of negative exponents here, but again, we're still just using our power rule as we've done for all of our other problems. So that 6 stays, x to the -2nd, we add 1. So -2 plus 1 is -1, divided by that -1, plus 8, the coefficient stays. X to the -3rd is going to become, well, -3 plus 1 is -2, divided by -2. And then x to the -4th, well, add 1 is going to become -3, divided by -3. And as always, can't forget about our plus c. Now this problem, we can have quite a bit of simplifying going on. So I'm going to first start with the coefficients. So I have in the first term, 6 divided by -1 is going to become -6, x to the -1st power. 8 divided by -2 is going to become -4, x to the -2 power. And I have a 3 divided by a -3, which is going to be -1, but I'm subtracting that -1, so overall it's going to become +1, x to the -3rd power plus c. So that's one option. However, as I've kind of discussed, a lot of times in calculus, they want you to have a positive exponent to your variable. So we would have to bring those variable terms back down to the denominator. So, but again, it's just the variable, right? It's only the x here that's being raised to the negative first power. The negative 6 is not. So that negative 6 stays in the numerator, and then x to the first comes down to the denominator. All right, negative 4 stays in the numerator, or you could write that as plus negative 4. I'm just kind of leaving it as minus 4, and the x squared comes down to the denominator, plus 1 over that x to the negative third becomes x cubed in the denominator, and again, finally, our plus c. So this, trying to be careful, that is how I would write our best final answer for this problem. Okay? Hopefully that was okay for you guys. Hopefully you were able to follow along. As always, please let me know if you have any other questions. And from here, you're going to move on to answering some Delta Math questions, just like the ones that we just completed. All right. Hope everything's well. Hope you guys are doing good. All right. Bye.